All right, this is Physics 1B for November 12th, and we're going to talk about the topics that are listed here. We're going to talk about processes for ideal gases and how to calculate certain quantities, and then we're going to move into talking about the second law of thermodynamics. Just to refresh what we did last time we worked a lot with one really kind of simple equation, and that equation was related to heat transfer. We talked about the idea that you could have some type of a system. The system could be like a closed vessel that contains a gas or something like that. We talked about what happens when heat comes in. We use the symbol Q for heat, and related that to the possibility that the system could possibly do work or something like that. Oops. Do work. And then we wanted to relate that heat that comes in versus the work that comes out to the change in internal energy of the system. And we used the symbol for internal energy we used was U. So this is what we call internal energy. And we could relate all of these quantities. So if we use W for work, Q for this, and U for internal energy, does anyone remember what the relationship between these three variables was? Simple kind of mathematical relationship. Yeah, it's actually the change. Yeah, you're right. It's the change in internal energy we talked about because that's more what we're interested in. And we said that the change in internal energy for this system is equal to the amount of heat that comes in or goes out. We defined the heat to be positive when it comes in and negative when it goes out, minus whatever work that the system does. And that relationship right there is called the first law of thermodynamics. It's pretty useful. We'll continue to use it today, even when we're talking about the second law. What we're really going to talk about now is smaller changes in these things. So a general, if there's small or infinitesimal changes that occur within a system, infinitesimal, then we're going to rewrite this equation as the change in U with a du, and then say that the system is going to take in a small amount of heat, dq, and then do a small amount of work, dw. It's not really any different at all. It's just replacing these things with, an infinitesimal, as they say. Okay. And the first thing we're specifically going to discuss are different types of processes, of which we'll see different applications as we move on. But just to get the terminology familiar with us and understand some of the, and specifically here I mean thermodynamic processes, so I could probably make that more clear. Types of thermodynamic processes in which you have some type of exchange of heat, and so these are thermodynamic processes. One other thing I want to mention is that the first law of thermodynamics effectively is a, restatement or equivalent to just the idea of conservation of energy. Every one of the terms within this expression right here is measured in joules, or can be measured in joules using the right units. So really what this says is that the change in internal energy is related to the type of energy associated with heat, which is Q, minus the work done, which is, work and energy have always been related to each other in all the classes that we've taken with physics, right? So types of thermodynamic processes. These words are probably words you've heard. I need to get my notes in a place where I can actually see them. Teaching this class is very different to me than teaching the other classes I've taught online, because I don't really use notes for the other classes. Like, I have organized plans, but I've done them so much that I don't need notes. I just need like general ideas, and then I can get from point to point, filling in the details as it is. But this is different because this is the first time I've taught this in probably 8 years. So types of thermodynamic process. Okay, the first one on our list here is adiabatic. Does anyone know what that means? I have a feeling, You've seen this word in chemistry before. Maybe you've seen it in physics before. I don't know. What does adiabatic mean? Does anyone know? Adiabatic. Your chemistry class, you probably talk about adiabats, which are like lines on PV diagrams, I bet. It's adiabatic process. Yep, no heat exchange, exactly. So for this one, we're going to say Q is equal to 0, or dq is equal to 0, either way. Adiabatic process is one in which there's no heat transfer in or out of the system. Which means Q is equal to 0, okay? And if we look back to our equation right here, if Q is equal to 0, then we know delta U is just equal to negative W, right? So in this particular process, delta for an adiabatic process, we're always going to know that delta U is going to be equal to negative W. In problems that you'll see, like they'll specifically say in an adiabatic process. So you'll immediately have to know. You said you're not, okay, Baron says, I'm not sure why, but I think that the temperature can change. Yes, the temperature can change. In general, if internal energy changes, there's a good chance the temperature changes because temperature is effectively a measurement of internal energy. It might not be everything to do with it, but with an ideal gas, one of the things we're going to say here in a little bit, which is a lot of what your problems are going to look at, the temperature change is the only thing that matters for change in internal energy. Okay? And you want to know why the temperature can change. So let's talk about, it doesn't always have to change, maybe, in an adiabatic process. It could be an adiabatic process in which okay, let's just talk about one example. So one example of this would be the compression stroke. In an internal combustion engine. If I write ICE and just say internal combustion engine, will you guys remember that that's what that represents? Internal combustion engine, which is the type of engine that you have in a normal car. That is to say, not an electric car or not a hybrid car. Even a hybrid car, I believe, has, here, I don't really know this is true, but I think it operates off gasoline, so some part of what it does is like an internal combustion. So what's the compression stroke? If I say that, do you know what I mean? Maybe you do, maybe you don't, I don't know. We're eventually going to be talking about this. I'm going to come down to this diagram right here. So this is kind of the end of class. We'll be getting more into detail about what's going on here, but this is the compression stroke. Let's just go through each of these pictures here because it's going to be helpful as we talk about these things. So this is a cycle of a 4-stroke internal combustion engine. Okay, there's a lot of stuff on this diagram. We're really just going to look at this piece right here, though. Okay. So you've got your crankshaft, your connecting rod, your piston. Here's your system, right? This is the system right here. There is a cylinder surrounding this, a piston that moves up and down right here, and when the crankshaft comes downwards, it intakes gasoline air mixture into the system here. So you're pulling in this substance, this tan or beige or whatever orangish substance, you're pulling that into your engine here with this stroke, okay? Once you have that substance in there, then the compression stroke involves basically the mixture being compressed. You were thinking isothermal? Oh, Andrew, I see you said constant. I missed that. Okay. So compression stroke. Intake valve closes, mixture is compressed as the piston moves up. So the claim is this is an adiabatic process right here. That's the claim, okay? That there is no heat exchange with the surroundings in this system right here. Does that seem reasonable? That if all that's occurring is a piston moves up and compresses the gas, the volume of the gas changes, right? But the idea is that there's no heat exchange with the environment. Does that seem reasonable? Can you think, feel free to be skeptical, can you think of any way in which, in this particular process right here, there might be some heat exchange with the environment. This, by the way, we're calling this piece right here adiabatic. We're saying that Q equal to 0, no heat exchange. Okay, so Barron says, quite right, through the walls if they are not insulated. Absolutely. You could imagine that heat would be escaping this way, right? If the whole thing is made out of metal, metal is a really good conductor of heat, right? So it's easily going to have heat kind of flowing out here and here, okay? But what if the process happens really fast? Which certainly it does inside of a car engine, right? I mean, these things are pumping thousands of times per second, per minute. Yeah, thousands of times per minute, right? RPM. Could be 3,000 RPM. So yeah, you can imagine that heat might be exchanged, but if it happens fast enough, then what I would say more exactly, and I think your book also says this is approximately adiabatic. And one thing that I think you'll find consistently is that if a process occurs quickly enough, if this is fast, so if this process is fast, then it's likely that the heat exchange with the environment should be approximately 0, relative to what matters, relative to the work that's done by the system, right? Relative to the other processes that are happening here, such as the work being done and the change in internal energy due to the compression, then, it's approximately adiabatic. It happens fast, okay? I think another example in the adiabatic process, I don't know if I can explain this one as well, because I don't know if I understand it, is when you open a soda bottle, right? So something that's been compressed, where the air has been compressed inside of it, right? I think that's also an adiabatic process as well. When you open, why would that be adiabatic? How about you guys try to? Why would that maybe be considered adiabatic when you open? What happens when you open a soda bottle? Let's say you've got a bottle of Coke that you just got out of a vending machine. What happens?
There's like a decompression.
It's a decompression. Why would you call it decompression? Pressure decreases. What happens to the gas inside though? Doesn't it? Yeah, like what Tom was saying, the compressed air is no longer compressed, right?
It starts to rapidly expand.
Yeah, the gas escapes, right? So I think that's also an adiabatic process because, like, think about how quickly it happens, right? Again, there's something about adiabatic processes. It means Q equal to 0, but to have no heat transfer in or out of the system, it usually has to be a fast process in order for this to occur, because you really can't stop heat exchange. I mean, you can try. You can insulate things really well. Okay, that's the other thing that happens, right, Tom? The CO2 in the soda starts to fizz, right? It's like the CO2 is kind of trying to escape from the gas, right? It's bubbling out of the gas, and some of it escapes out the top, okay? So something happens. The internal energy is going to change in that process. Let's see, what would the work done be in this case? The soda loses its volume goes up, right? And if the volume goes up, I don't know, this is another thing we learned last time. How do we figure out work? How is it related to volume? The work done is generally the pressure multiplied by the change in volume, right? You have to kind of integrate here in case the pressure is a function of the volume. But if the gas expands as the soda bottle is opened, then I would think that the work would be positive, right? Because the volume, if dV is positive, then dW would be positive. So then that means the change in internal energy would be negative, which would mean a temperature decrease. Does that seem reasonable? How could we associate opening a soda bottle with a temperature decrease? Maybe the gas above the soda actually decreases in temperature as it expands. The book mentioned something, and they mentioned something about seeing like a poof of like smoke, not smoke, but like water vapor that happens at the top of it when you open a bottle. You do see that, right? Especially if it's really cold when you pull it out. You can see it even when you open like a soda can. I have a soda can. I kind of want to open one now and watch. But you'll see like what is that? What is that poof of what are you seeing there? I think I know what it is, but what do you think it is? I hope all of you can imagine what I'm talking about here. The idea is like right above the soda can, you'll see cold air. Okay, what about cold air? Why do you say cold air? What is that? What are you thinking about? You ever been on like a top of a mountain or somewhere cold and you see your breath? I think it's kind of similar to that. I think it's like similar to you seeing your breath. I think it's like condensed water vapor. Condensed gas expanding. I think so, but I think like I was talking specifically about the fact that if W is positive, then delta U has to be negative. And if delta U is negative, then in this process here, I think that delta T is also negative. Right? Because if the internal energy goes down when it expands, it must cool. And if it rapidly cools, I think that's what you're seeing with that like poof of smoke. I think it's water vapor, really. I think it's condensed water vapor. I think. Or maybe it's condensed CO2. Maybe it's like dry ice. I don't know. I should probably investigate this before talking to you about it. But like dry ice has that same effect, right? It converts directly from the solid to cold CO2. And what does it look like? It looks like kind of like that poof of smoke you see when you open a soda bottle. Okay, so those are examples of adiabatic processes. What else do I want to say about them? I think that's it. That's all I want to say. I believe this is the main type of process, or one of the main type of processes that we're going to be see showing up over the next chapter or so in terms of problems. Okay, so that's number one. Let's use a different color for the second one. All right, so let's use gray. Let's not use that color, actually. Okay, so the next process is isoquark. This is one I do not remember from. I mean, I kind of that word just doesn't seem familiar to me. Does anyone know what isoquark means? You know, actually, opening a freezer is probably probably an adiabatic process as well. Because like right when you open it, you see all of the gas inside expand out.
For isoquark, is it a constant volume?
Yeah, that's exactly right. This is a constant volume process. So if it's a constant volume process, and again, we go back and we think about this equation right here, that the work, remember this is work on this side. Not work. And this says pressure times change in volume. If the volume is constant, then that must mean that the work done by the gas is 0. Or the work done on the gas is 0. See now those words I recognize. So Baron is saying isometric or isovolumetric is also used. Those look like words I've seen before. Yeah. So your book chooses to use isoquark, which is fine. We just, as long as we all agree that what we're talking about is a constant volume process, I suppose it doesn't matter which word we choose here. But in this case, it's a constant volume process. Volume doesn't change, so the work done by or on the system is 0. Or and if the work done is 0, then in terms of the first law, again, delta U is equal to Q minus W. In the first process, Q is 0. In the isoquark process, W is 0. So that means any internal energy change associated with this process should be equal to the heat input or output to the system. So for an isoquark process, we get that relationship there. For an adiabatic process, we got that. So the change in internal energy in a constant volume process has to be exactly equivalent to the heat exchange. Does that make sense? constant volume process could be, so I guess a simple example of this would be, if you have a closed system, so that heat can't really, well, I guess it's okay if heat can escape. Doesn't really matter. But as long as it's closed so that the volume remains constant, so you have a fixed volume. And it could be insulated or non-insulated, I guess it doesn't really matter. So inside of here, you've got some gas molecules. And if you wanted to have an isoquark process, then what you could do is you could just heat it up, right? You could have some kind of a hot plate down here. And you heat it up. So then you have energy coming in. The volume doesn't change because the volume's fixed. As the energy comes in, it might increase the pressure, it might increase the temperature, but the volume won't change. Okay, so that's an isoquark process. All right, next, isobaric. You want to know what isobaric means? What does the bar part represent? Isobaric.
Constant pressure.
Yep. So this is a constant pressure process. So any process that occurs at a constant pressure. So if pressure is constant, then our equation that said that dW was equal to PdV, if we integrate both sides of this and the pressure is constant so we can pull it out, then this equation simply becomes the work done is equal to the pressure multiplied by, and this would be some volume change occurring here from some volume V1 to V2. So this would become just pressure times V2 minus V1. So that's an isobaric process. Any questions about that? What's an example of a constant pressure process? Can anyone think of a constant pressure process? Maybe think about like cooking. So I think take the same example that we just did over here, but replace the thing inside of here with a liquid so that the volume can't really change, right? Liquid's volume tends to stay the same. Pressure cooker. Yeah, probably a pressure cooker. But I was just thinking, like, say you're boiling water. So you've got some heat source, and you've got water, and you're boiling it. Then the pressure should be constant because you're subject to atmospheric pressure, and maybe there's a little bit of difference in pressure at the bottom, but overall the water has constant pressure. So, yeah. All right. Last one is isothermal. So isothermal is going to be constant temperature process. So if it's constant temperature, then the internal energy should be zero. So delta U, the internal energy should be constant. So delta U should be equal to zero, which leads to any energy that comes in through heat should be equal to the work done by the system for this one. So that's for a constant temperature process. And those are the types of processes: isothermal, isobaric, isoquark, adiabatic. I feel like we're going to spend most of our time talking about this one. But there will be we'll discuss, as I said, how an internal combustion engine works. And while the compression stroke happens to be adiabatic, some of the other strokes are going to be some of these things. And we can kind of rely on what we learned here. So the key thing here is adiabatic, change in internal energy is equal to the negative of the work done by the process. Isoquaric, change in internal energy is just equal to the heat that comes in. Isobaric, work is this. And then for an isothermal, we get this one. Heat comes in is equal to the work done. Any questions? All right, so the next topic is internal energy and ideal gases. So this is going to be kind of a important idea that we're going to take with us and use from time to time to do little proofs. So this is going to be a kind of a first principle, so to speak, for thinking about thermodynamic systems. So for an ideal gas, we want to talk about what's called free expansion of an ideal gas. Free expansion means one in which the ideal gas doesn't exchange heat with its surroundings and it doesn't do work on its surroundings. So it's just kind of free to expand in an open setting. Okay. And the kind of diagram for what this would look like would be, suppose we have some kind of a container. It's closed, probably insulated from its surroundings. And within the system, we're going to have a barrier, but it's going to be kind of a weak barrier. And then in the bottom of this, we're going to have gas molecules. So down here, we have gas molecules that are zipping around all over the place. So all these molecules, they're zipping around. So we've got gas inside of here. It's an ideal gas at some pressure and some volume, right? And then up here, we just have a vacuum. So there's nothing up here. And then due to the pressure of the gas down here, we're going to say that it's going to break the barrier. So this barrier is going to be very weak. And due to the pressure of the gas down here, it's going to break the barrier. But we're going to assume that in breaking the barrier that it does an extremely small amount of work to break the barrier. Okay, so the barrier is going to break. And then we're going to have what we call free expansion. The gas will, as gases tend to do, fill up the rest of the volume. So the gas is now going to have a larger volume. Probably its pressure goes down, right? I think it has to, right? If the volume goes up. So what would we say here? The volume increases. But it does so in a way that it does no work. Normally it would. The pressure decreases since it's occupying a larger volume now. Pressure decreases. But what experiments show for processes like this, well, I guess the question would become, what do you think happens to the temperature now? Those are our three state variables, right? Pressure, volume, and temperature. They describe the properties of any type of a... Temperature might go down. Does anyone think it might go up? Remember, the system is closed. It's insulated. The fact that it's insulated means that I believe Q is going to equal 0, right? Q represents heat exchange. So we're assuming no heat comes in, no heat goes out. We're saying that as the volume increases, that somehow it does no work in that process. So it turns out that the temperature actually stays constant. So the temperature... So I'm just going to say temperature stays constant in experiments. That's my way of saying that in investigating ideal gases, when people reproduce this type of a experiment, experiments show that the temperature stays constant. The temperature stays constant. And that happens specifically for ideal gases. So given that this is true, for an ideal gas, we can say that the internal energy is only dependent on the temperature. And that's the kind of biggest takeaway from this, is that for an ideal gas, the internal energy is only dependent on the temperature. We're going to use that idea multiple times in this class. I want to say it the right way. For an ideal gas, the internal energy only depends on temperature. Not pressure or volume. It only depends on temperature. We can think of this as like a, I don't know if calling it a postulate is the right thing to say. It's not an assumption. It's something that's experimentally verified. But when it comes to, what am I trying to say? When it comes to sometimes experiments can be wrong, I guess is what I'm trying to say, right? It could be the case that we're missing something here, but every experiment that we've done shows us that this seems to be true, so we can just go ahead and assume that it's true. Does that make sense? This is something that's done, I mean, this reminds me a lot of Einstein. A meta-assumption, Baron? Yeah, I like that. Maybe it's a meta-assumption. And it's something we need to assume to do some of the kind of things we want to do. It reminds me a lot of Einstein. Einstein, when he was talking about the speed of light, what he said was, we think the speed of light shouldn't be constant, but every experiment we've done to measure the speed of light seems to show that it's constant. So let's just assume that's true. You know, that's when experiments keep showing you over and over again that something's true, even if it goes against what you believe should be true, then maybe it's a good assumption. Maybe you should just make that assumption. All right. So again, this is just for ideal gases, and for non-ideal gases, I believe that this is not true. Specifically because for non-ideal gases, there are going to be interactions between the particles. Remember, I wasn't trying to expand that. I was trying to say, so you've got different particles here, right? And for non-ideal gases, you're going to have some attraction between these things. And that attraction is going to be a type of internal energy. And since it's an attraction that's based on the distance between the molecules, that means that attractive force would go up in this case because the molecules are closer together. They're in a smaller volume. So for a non-ideal gas, one in which we assume that there are interactions between the particles, this is not true. And the internal energy will depend on pressure and will depend on volume. If you put it into a smaller space, there's going to be more interactive forces between the particles, and that will then increase the internal energy, which means that the pressure and the volume are going to affect the internal energy, basically. Right? I think I got that right. Yeah, so if you replace this with an ideal gas, who was it that said it? Yeah, Tom, I asked, what do you think is going to happen to the temperature in this case? And Tom's assumption would be that it would go down. And for a non-ideal gas, that would be true. So if this was a non-ideal gas, the temperature in state 2 here would be less than the temperature in state 1. Because the particles are farther apart, so that means that there's less attractive forces. And yeah, so your natural kind of assumption about what was going on there is accurate. Okay. Okay. So, now for a bunch of math. All right. So, now what we're going to do is talk about heat capacities for ideal gases. And we're going to need to use this idea here along with the other things that we've talked about to do this derivation. So, specifically now we're going to be talking about heat capacities for an ideal gas. This is something we've talked about before. We've obviously talked about heat capacities. And just to refresh how we discuss these things, we said that for an ideal gas, you have heat capacities, and there's two different heat capacities. There is a heat capacity at a constant volume, and there's heat capacity at a constant pressure. Okay, so this was heat capacity for constant volume. And then Cp would be the same thing but constant pressure. So heat capacity at constant volume and heat capacity at constant pressure. Those symbols right there. And each one of them we can use to talk about the heat transferred in terms of the heat that comes in and how it relates to temperature change. So for the for constant volume, the amount of heat that gets transferred was equal to the number of moles multiplied by this constant volume heat capacity, and then multiplied by the change in temperature. This equation is, it doesn't look the same, but what you should be thinking of is specific heat, right? So for specific heat, we said you take the mass of the object, you multiply by the specific heat, and you multiply by the temperature change. But we also said there's another version of this where you multiply by the number of moles, and then the molar, so capital C represents the molar heat capacity, right? I could even put that up here just to remind what I'm talking about. This is the molar heat capacity at constant volume. So then for even a solid, you could have molar heat capacity. Just change your mass to the number of moles and then multiply by a heat capacity that's appropriately turned into the right units to make it work. Okay, so very similar relationships. And for our I may have written down this equation too quickly here, actually, now that I look at this. Yeah, I want to say something else before I use this, but we will be using this later, so I'll just pull this down here. But that was the relationship we had for these type of systems here. All right, so the question that we want to kind of answer here is, why are these values different? If you go into a table and you look up the molar heat capacity at constant volume and at constant pressure, you're going to find different values. In fact, you're generally going to find that the heat capacity at constant pressure is greater than the heat capacity at constant volume. So for this, we can rely on the equation for the equation for the first law of thermodynamics. The first law of thermodynamics says that the change in internal energy in a system is equal to the heat that comes in minus the work that's done by the system. So that's the first law, right? So as far as molar heat capacity goes, if we think about constant volume, what happens to this equation here when we talk about constant volume? What can we say about it? Are any of the terms zero if the volume is constant? No work, yeah. So constant volume means that the work done by or on the gas has to be equal to zero. You can even say dW is equal to zero. But remember, this is just the work done is equal to zero. So constant volume, and that's because, and again, I'm just going to write some more equations over here just to reference, the work done is related to a volume change. You can't do work if the volume doesn't change. So the work done here is zero. The work done here is not equal to zero, right? The work done in this case has to be equal to just what we wrote over there. It has to be equal to the pressure, which is constant, multiplied by dV. But because it's constant pressure, we'll leave it at that. All right. So the question now becomes, why is Cp greater than Cv? All right. And the simplest answer would be that since we can rewrite this equation here and isolate it for dq, this equation would become the change in the heat change, or the heat that comes in, should be related to the change in internal energy, but you also have to add to that any work that's done, right? So in the case of constant pressure, because you have this extra term right here, then the dq has to be 0, has to be greater, right? Does that make sense? I feel like I explained that in a really complicated way. If you look at this equation, and then we look at this equation here, so the equation for constant pressure is going to be just exactly the same, but you replace big CV with CP. Right? So this dq is equal to du plus dw. This dq is equal to du plus dw. But the difference is that this is 0. And this one is equal to du plus dw. But dw is bigger. Zero versus something. So this means that basically CP is going to be greater than CV. So how much bigger is it going to be? All right, well, what we can do is we can kind of expand out this equation right here. So this equation says that du plus dw, and dw is going to be pdv, pressure times the change in volume, should be equal to dq, which is this thing right here, N times Cp times dt. All right, so now I'm going to say is that if we look at these two equations right here, what we have on the left-hand side is that if we calculate this quantity here, it's going to be related to the change in internal energy of the gas, right? So even if I'm talking about a process in which the pressure is constant as related to the Cp right here, the change in internal energy, here, it's still on the screen, right? For an ideal gas, internal energy only depends on temperature, not P or V. So a change in internal energy is also dependent only on temperature and not P or V. Okay? So what we can do is we can replace the du here with this expression here. Because regardless of if we're talking about a constant pressure process, the value of this quantity here should still be equivalent to this value here, because, you know, it's an example of how dt is related to the change in energy. So you can basically just replace this with du right here. Did that make any sense, or did I confuse you? Considering all the math on the screen, I'm sure that's a little confusing. So if you have any questions, feel free to ask. Sure, yeah, take some time. Oh, I actually have a picture I realized that I didn't include with this. Maybe that will help a little bit. Let me put this picture right here. Let me move some things around. I'll fit in right there, I guess. We're gonna, yeah. So we want to prove, we already kind of proved why this is true. Your question is showing why CV is greater than CP. It's the other way around. CP is greater than CV. But we also want to know what their relationship is. We kind of want to know what the ratio of them is. So these are two different processes here. we're measuring the molar heat capacity of an ideal gas at constant volume and constant pressure. So for constant volume, we have this relationship. Heat added is dq. There's n moles of gas. It's in a closed container. So that means that the temperature has to go up. And this tells us exactly how much heat is added and how it's related to the temperature change. For a constant pressure process, you have a container with a movable piston that applies constant pressure. You add heat, and in the end, the effect is the same. The temperature of the system changes, right? So constant volume process, constant pressure process. Now what we want to do is we want to compare the two processes and say the one thing that they have in common is the change in temperature is the same, okay? So we look at the constant pressure process here. And if that equation looks complicated, remember we started from the first law of thermodynamics, right here. In the change in internal energy is equal to the heat that comes in minus the work that's done by the gas. We rearrange this to say dq is equal to du plus dw. And then from there, we started replacing things. So we replaced dw, which is the work done by the gas, with the constant pressure of the gas times the change in volume. That is to say that the piston moved upwards, and therefore there was work done by the gas, and the amount is PdV. The heat exchange is going to be related to a temperature change. As the heat comes in, the temperature of the gas increases by some amount that we call dT, right here. That doesn't change in this line. So the only thing that changes now is to say whatever this quantity du is, the change in internal energy of the gas, if the temperature change in both cases is the same, then we can look at what happens in this is the constant volume over here, and say whatever the change in internal energy, since it only depends on temperature, and I have an expression for how much the internal energy changed by right here from my constant volume process, then I can just pop it right there. Numerically, these have to be equivalent to each other. And so that's how we get this relationship here. And what's nice about this is it directly relates CV to CP. And that's ultimately what we want to, find a relationship for. Okay, does that make more sense as we went back through it there? It's kind of complicated. Okay. So, PdV. What I would like to do next, and maybe you can predict what the next step in this process is, I would like to eliminate, you notice this term has an n and a dt, this term has an n and it has a dt, and we'd like to eliminate those. So how can we write the pressure so that it involves n and dt? How can we relate the pressure?
Oh, it's just the ideal gas law.
Yeah. So the ideal gas law tells us that, PV is equal to nRT. So we can replace, what we want to do here is, if we're talking about, sorry, this looks confusing because I'm mixing these together. Let's just come over here and kind of go down. Pressure's constant, right? So my ideal gas law, what I can write it as then is, if only the volume is changing and only the temperature is changing, I can just replace dV and V with dV and T with dt. N is the number of moles, which is not going to change in this process. And then the pressure was constant. So basically P is going to end up being equal to, or, well, you can see it. That's PdV right there. So we don't need to do anything else. We just go ahead and replace it. So we end up getting N CV dt plus PDV gets replaced. Let me erase this piece. PDV gets replaced with nRDT. And that's equal to n times CPdt. And now the n's and the dt's all cancel. And you get this really simple, this is a shockingly simple relationship. The molar heat capacity at constant volume plus the gas constant, the ideal gas constant, is equal to Cp. That's a really simple relationship. So, complicated derivation, nice simple relationship at the end. And what we're going to do is we're going to rewrite this by using a ratio. So we're going to let the symbol gamma, the third letter in the Greek alphabet, be equal to the ratio of these two quantities of Cp over Cv. Remembering that Cp being greater than Cv, this is always going to be greater than 1. It's guaranteed to be greater than 1. Maybe it could be equal to 1, I don't know. But it's always greater than 1. For a monatomic gas, for example, Cv is equal to 3/2 R. I don't know if you remember why this was the case, but basically the molar heat capacity ended up being related to the internal energy, which was related to the temperature, and the temperature was related to the number of degrees of freedom. And for a monatomic gas, it had 3 degrees of freedom, motion in the x direction, y direction, and z direction. And that's where that shows up. I believe for a diatomic gas, it was Cv is equal to 5/2 R. Anyway, so if Cv is equal to 3/2 R, then we can calculate what Cp is. Cp would be equal to Cv plus R. So Cv is 3/2 of R plus R. This is going to be equal to 5/2 of R. And then we can calculate what gamma is. Gamma, again, is just a simple relationship between Cp and Cv to kind of simplify some of our calculations. So for this, gamma would be equal to Cp is 5/2 R. And then Cv was 3/2 R right there. So gamma is equal to 5/3, which is approximately 1.67. I think gamma for air, because it shows up in a lot of your problems, is 1.4. Just air, like atmospheric air. And I believe I have a table. Okay. So this is molar heat capacities at low pressure. Let me see if I can get all this stuff on the screen here. Let me just zoom out a little bit. All right. So let's see if any of this stuff is true. So monatomic gas, helium, it says that Cv is equal to 12.47 and Cp is equal to 20.78. Also for argon, apparently they have exactly the same values. And if you do Cp minus Cv in this table right here, you end up getting 8.31. 8.31 is the gas constant, right? And then the relationship of Cp over Cv ends up being 1.67 over. For diatomic gases, H2, nitrogen, oxygen, carbon dioxide, Cv is 20.4, Cp is this. Again, if you subtract them, you get this. And for these, gamma is equal to 1.4. Maybe we can understand where this comes from. Maybe we could figure out what this comes from right here. So gamma is Cp over Cv. And I believe that Cv for this was, if what I said was true, right? Maybe I'm just misremembering. I think for diatomic, let's see if this works. I think Cv was equal to 5/2 R, which means Cp would be equal to, you add an R, so it's going to be 7/2 R. So then that means that gamma is equal to basically, 7/2 divided by 5/2. R's cancel. So you get 7 over 5, and 7/5 would be like 1 plus 2 over 5, which is, yeah, exactly 1.4. And then I believe with polyatomic ones, it looks like the relationship we got here doesn't exactly hold anymore, right? While for diatomic and for monatomic, the difference between CP and CV is 8.3. Doesn't look like that's nearly as true as much anymore with the polyatomic gases. So there we go. One thing to emphasize about this is that we did use this relationship, which means that what we derived here should really only be true for ideal gases, right? And so perhaps these polyatomic molecules are more polar, and as a result, they may have more interactive forces between them. So these are probably not considered to be ideal gases at that point, right? To some extent, you could use this as a definition of an ideal gas now, right? Like if you go and measure these quantities, which how would you measure them? Well, you'd get some quantity of this substance, right? You'd add a fixed amount of heat to them, and you'd observe the temperature change. And you'd use that to calculate what CV is. So you can determine these quantities here in an experiment. And then once you've determined them, you can subtract these. And if the value you get is 8.31, then the gas itself must be monatomic, basically. Sorry, not monatomic. It must be an ideal gas, excuse me, right? That's basically a measurement of ideal gas, is if the difference is exactly this. But if it's not, then it's basically not an ideal gas. That being said, we can still measure gamma, and we can still use it to do calculations, as we'll see here in a little bit. All right. I think that's a pretty solid place to stop. And I think when we come back, we will do one of these problems. Although I gotta make sure. I think we can do this one. For the next one, though, I think we need to do a little bit more work. I'll check to make sure. But what we'll do when we come back is we'll solve this problem here. And I'll just say that we're taking a break until 11:02. I'm gonna stop the stream.